Now we don't want to count our chickens before they've been dashed with a sprinkle of chaos magic, so running that, we see that behind the scenes the silly and surly were actually encoded by compressed silly and compressed surly. So the takeaways from this example is that when you have the left shift C operator, you're going to see silly, and when you have the right shift, you're going to see surly. But specifically, these shifting by an immediate implies that the compiler must know what the immediate is at compile time. And indeed, we can see that here is the 4, here is the 3, because the compiler knew that these were going to be the values specifically used for this code. If the compiler didn't know the value ahead of time, then it wouldn't be able to use these instructions. So we pick up silly and surly, but we also have silly and surly over here. So there's a 64-bit version and there is a 32-bit version. Why do you have the two same named things in two different columns when we know that all 40 of these assembly instructions should be ostensibly usable as a subset of the RV64I? The answer is because, again, when it's silly being operated in 64-bit mode, it's assuming that it's operating on 64-bit registers, and therefore the shift is having 6 bits to encode the immediate rather than only 5 when you're operating on 32-bit registers. So whereas all these other instructions like add and subtract and XOR and OR and all of these other instructions can be used in 64-bit mode, and they just kind of do the right thing because they're defined in terms of xlang, the 32 or 64-bit registers. But because these need to do a different indication of how many bits to shift based on 32 or 64, they are actually different instructions, even though they share the same names. All right, and on our diagram, we're going to start a new section here for shifts, and we're going to collect 18 shifts before we're all done with it. These count as 2, the 32 and 64-bit version, and then we've got our compressed silly and compressed surly.